Okay, good morning. So last time we talked about so-called switched capacitor circuits. They're not in the book because sometimes they're considered, well, sort of advanced material. But we have seen that actually pretty simple, and probably you will agree with me at the end of this lecture that they are actually simpler than circuits that have resistors and capacitors we will talk about today and involve differential equations and so on. Anyways, aside from being simple, switched capacitor circuits also can do many of the really interesting things that electronic circuits are able to do. We looked at the idea of a touch sensor, right? Capacitors, they provide the interface between our finger and the computer. How in the world does an electronic system know what a finger is? Well, it doesn't really, but it can see capacitance because our finger is mainly water. The electric constant is much higher than that of the air, so if we put the finger on the touch screen, well, the capacitance changes of wires that are invisible, right, made of ITO, and then we can build a circuit that, for example, can use a switched capacitor approach to actually measure the capacitance and detect whether fingers there or not. Other things that we've looked at were digital to analog converters, and again, they're very important because all these MP3 players, phones, and all of that stuff wouldn't work if we didn't have those circuits. All right, and so we could look at how they are built. Actually, those are usually made as integrated circuits, not always, but usually made as integrated circuits. And just somebody asked me about, well, how this curriculum go on, and yes, if they don't want to know more, then you would go into 105, 140, and so on, and hear a lot more about that. But we can already understand a lot of what's actually going on in these circuits. But now, let's go and face sort of the challenge and look at RC circuits, so circuits that consist of and capacitors. Okay, and we will get at the mathematical treatment of that. And if you look at the book, you will see that it has a lot of math on how to deal with these circuits. You will probably have to go through quite a few of these examples in order really to appreciate that. But just as important it is to have an intuitive circuit type of idea of what's really going on. So here we have a very simple circuit, has a source, a resistor, a capacitor, and it still has a switch. The switch is simply there so that we can somehow define an initial condition. The initial condition here is that the time equals 0, the capacitor C is discharged, and then we close that switch. Well, of course, if we close that switch, we have now connected the voltage source through the resistor R1 to our capacitor. What's going to happen? Yeah. Okay, right. So, and then what happens with the capacitor? It gets charged up. Okay. All right. So the capacitor gets charged, and then, of course, the voltage initially is what? Yeah, 0. Initially 0. Why? Well, because I told you that the capacitor was initially discharged. So we start out here at time equals 0, right? So this is a little bit a contrived example, of course, much like many of those in the book. We start at 0, and then the capacitor gets charged. So if we wait for a very, very long time then, where does the voltage go? What does the voltage reach ultimately? V1, right? It does not go to infinity or something like that. It's just what really happens is that initially, what is the voltage drop across the resistor R1? Just when we close the switch. That voltage drop is V1 because on the left side of the resistor we have, well, V1. On the right side of the resistor, the capacitor is discharged still. We have 0, so the voltage drop across that resistor is V1, and consequently a large current flows. But then, then the voltage VC1 is going to increase, and what happens to the voltage across the resistor? It will decrease, right? And consequently, the current I1 also decreases, and consequently we charge the capacitor still, but we charge it more and more and more slowly until ultimately the voltage on the capacitor reaches the value V1, and then the voltage drop across the resistor R1 is 0, right? And the current, of course, is also 0. It's very useful to go through this kind of thinking and have an intuitive understanding what the circuit actually does. In fact, when I solve this type of circuit, I always first make these plots. Whether or not they are asked in the assignment, who cares? I make these plots for myself, and then I go and solve and go through all the math and probably make a mistake, and in the end I get a result and say, well, that result doesn't match what I plotted there, and I find my mistake. So I recommend you might consider that also. All right, so we start out at t equals 0, and ultimately we end up at voltage V1, and in between we sort of increase the voltage first fast, and then more and more slowly because the current I1 decreases. Okay? And the same thing happens also here. We start out at the current V1 over R1, and we end up at the current that is 0. Of course, how long does it take to get to exactly 0 with the current? Infinitely long, right? So it's asymptotic, but then we get so close that, we're engineers, we are not mathematicians, so we get to essentially 0 rather quickly. Okay, so this was the intuitive solution of this. And although, again, in the homeworks, and especially on these online homeworks, it doesn't tell you to plot this because the computer has no way, or at least that system has no way to understand what such a plot is. So, but even if it's not asked, I suggest go and do this, because it will be a lot easier afterwards to understand what the circuits are really doing than if it just grinds through the math and all these equations and so on. At least for me, that's hard. Okay, so, but now we are going to actually do the circuit analysis. And let me first redraw the circuit. Just when the switch has closed, the circuit looks like this. I mean, it's exactly the same as we have before above, but it's just a little bit easier to see what's going on here if the switch is not present. Okay, so now we want to solve for the voltage VC1. Okay? So how we're going to do that? Well, why not? Let's use node voltage analysis. For which nodes do we have to write an equation? Just for this one, right? VC1, the other node V1, of course, the voltage is given. So it's one single equation that we'll have to write. We'll see. In the end, we're going to end up with two, but essentially it's one single equation. So we have currents, again, IA, and we have current IB, and the sum of these must be 0. Hey, we did that many times, right? Okay, so, well, IA, that's fairly easy. What is that? VC1. And now, that's another thing that I often do. I show that VC1 is actually a function of time, right? It's going to change this time. VC1 of time minus V1 over R1. Okay, so that was easy. What about the current IB? Okay, so some of you paid attention and read the book and so on, but let's get on that. So for the capacitor, the charge on the capacitor is Q1 equals C1 times Vc of t. Okay? Now let's take the derivative of this equation. What is dq dt? Right? So that's I1, which of t. So I guess I should have said of t here also. I1 of t, which happens to be IB of t, which is equal now to C1. C1 doesn't change with time. It could be, but in our case, it doesn't change with time. So the derivative is just C1 again. And Vc, well, it changes with time. We don't know the shape yet. We want to figure that out, right? So I have to write Vc of t dt. Okay? So now we need to copy this here, C1 times dVc of t dt, and this is equal to 0. Okay? So that's the equation that we have. Now, for those of you who remember the mass and so on, can we solve this equation already? Do we know enough? What else do we need to know? Yeah, some kind of an initial condition or boundary condition, some point, right? Otherwise, we have a shift. What is the voltage initially? Well, I told you that initially the voltage is Vc1 of t equals 0 is actually equal to 0. Okay? So now basically I've told you everything. Right? The rest is mass, and mass you took in some mass 1A or B or somewhere in high school, and you're done with that. This is how we write these equations, exactly the same way as we wrote them for resistive networks, except that now if we have a capacitor, we have to use that differential equation, well, and the whole thing becomes a differential equation. And again, you basically know already how to do that for mass. Now, I'm going to tell you how I solve these, okay? Which is perhaps a little bit different from the way you've done it in mass, and a little bit less general, but it works well for me, so you may want to consider that also, or whatever you like. Right? So what I did here is I rewrote the equations that we just had on the previous page. So this is the differential equation we had, and then on the right side we have that initial condition. And it looks slightly different from what we wrote on the previous page, simply because I rearranged the term, pure algebra. Okay? So now, again, there are lots of ways on how to solve such differential equations. I say, hey, you know, I'm a circuit designer, and I kind of know what my circuits do, so I'm going to be very good at guessing. If I look at this, what's the top red curve probably going to be? An exponential, eh? And the bottom one, well, it's probably going to be an exponential. So why don't I tie with an exponential? So then I juggle my exponential terms around a little bit like this. So I know that the voltage, it needs to start out at some fixed value, happens to be V1, right, in our example. And then afterwards it has dropped down to 0. And e to the minus t over some tau, whatever that is, right, just from units, there got to be something there. I cannot make e to the minus t is meaningless. I hated the teachers who made that. Is it seconds? Is it hours? Or whatever, right? So e to the minus t over tau. Well, for t equals 0, actually, what did I do here? Yeah, no, we start out at v equals 0. Yes, we start out v equals 0. So we are this point, right? Okay, so e to the minus t over tau for some finite tau at t equals 0 is 1, right? E to the 0 is 1, right? And so that wouldn't do the right thing. Actually, that would be fine for the current, perhaps, but it definitely would not be fine for the voltage. So I somehow need to make that 0. Well, 1 minus 1 is going to be 0, right? 1 minus e to the minus t over tau is going to be 0 for t equals. I end up at some voltage, so I need to have some constant in front. Let's call it A, that will have unit volts, right? And let's try with this. So how do we try? Well, we then actually compute the derivative here, okay? And then we plug all of this into this equation up here, okay? And what we get is this, okay? And now if we look at this equation, first of all, this thing we already know is going to have unit volts. Tau is going to have what units? Seconds. Fortunately, this thing has also units seconds. But because A has units volts, there is no way to make this equation be satisfied but set tau equals to R1C1. So tau must be equal to R1C1 here. Otherwise, the units are never going to work out because we cannot compensate seconds with volts or whatnot. Okay? So that's what we have the first thing. Then we know that for time equals 0, this whole thing, Vc1, must be equal to 0. So let's just plug in time t equals 0. So then this term actually becomes 1, and 1 times a is a, right? A equal, and this one becomes 0. So this whole thing here becomes 0, right? Because e to the minus t over tau is now 1, and 1 minus 1 is 0. So a equals 1 in the end. If you carefully at this, you get a equals 1, okay? So now we know the two unknowns in, this is our final result here. We know the two unknowns, a and tau. We have the final result, okay? So simply by guessing what should be the right answer and then plugging in and comparing coefficients, and so we could solve this differential equation. Yes?
Can you explain again why it's R1C1 tau? You just go over that one.
Okay, so this whole term here, the unit of this whole term must be volts, right? Got to be volts. So this term here has unit seconds. This term here has unit seconds. Right. Yeah. So how can I possibly, if I end up with extra volts or so, or extra seconds, if I don't make these two terms cancel out?
But then, like, what if tau is like 1/2 R1C1? Then you just have a multiplicative factor of like 2 or something. Like, I can see your solution works in by uniqueness of solution, but it's.
Oh, okay. Yeah, you're right.
Yeah.
You're right. Well, could we? Well, basically what you want is a proof that tau must be equal to R1C1 and not some multiplicative factor times that.
I think the proof is just that there's only one solution. This is a solution, so this has to be the only one.
Probably.
Yeah.
Probably. At least the result is true. Huh? This is the only solution. You can go try another. I was going to say, go try another one and see where you run into problems. So you see, I'm not a math teacher. This works for me, but if you want to know what's going on in the math under the hood, go ask your math teacher. Okay, so that's how I solve this. Okay, so now of course we can make examples and so on, and lo and behold, if we use this equation, right, that we now got on the previous page, and we plug in some values for R's and C's, incidentally they determine now that tau, and we use a computer program to plot this, we get exactly what we already said we would be getting. We're getting a curve that looks like this, right? That's what we end up with. Do something interesting with this. So at the very end, this capacitor is charged to what voltage? V1. And so what's the energy on this capacitor, C1? Yeah, 1/2 C1 V1 squared. Okay? So, question, what is the energy actually delivered to this circuit by the source V1? Yeah, right? He's right. Huh? There got to be more. Why does it have to be more? Why does it have to be more than this? Yeah, there is this resistor in there, and that dissipates power. How are we going to figure out? Yeah?
Integrate the power dissipated by the resistor.
Yeah. Yeah. Or actually, or even let energy delivered by V1, that would be the power, first of all, as a function of t of source V1, right? That would be equal to V1 times I1, which is a function of t. Well, what is I1 of t? Well, we know that now. That is equal to V1 minus Vc1 of t, which we know, right? Which we just calculated, divided by R1. And if we go a little bit further here, we get V1 squared over R1. And this V1 minus Vc1 of t, that just sort of cancels, and we end up with e to the minus t over tau. Tau, okay? So incidentally, this is again exactly what we expect, right? Because we had said the current is an exponential that decays, okay? And here that's what we really have, right? That t equals 0. Well, the current is equal to V1 over R because e to the minus t over tau for t equals 0 is 1, okay? And then, of course, if tau goes to infinity, well, e to the minus infinity is 0, so the current drops down to 0. All right, so then afterwards we have to do a little integral. The energy of t, of time capital T, is the integral of from 0 to t of p of t dt. And now we want to make t go to infinity. Another little math problem. I'll let you deal with it. The result that I got, so I plug the equation up here in and I do this integral and so on, is I get C1 times V1 squared. Did you expect this? Is this remarkable? Well, why don't, so yes, we don't have the 1/2 anymore, right? That's the right thing, we have to compare it. So we use this kind of a circuit to actually charge a capacitor. And we already said, well, we probably are going to lose some energy in the process because there is this resistor there, right? But, and now this thing net tells us, well, the energy that's delivered by the source is larger than the energy that we have at the end on our capacitor. Actually, it's how much larger? Exactly twice. Huh? It's exactly twice as much. So apparently what's happening here? Huh?
Twice as much is irrespective of the resistance, so that's true for any resistance.
Exactly. Right? Isn't that remarkable? That the resistor doesn't show up here. Apparently, no matter what value I choose for this resistor, half of the energy is going to be lost in the resistor, and the other half actually ends up on the capacitor. Yes.
How does that make sense, though? Because you can have a non-ideal wire, and that has a very low resistance. But then, if you say an ideal wire, that has zero resistance, and then not see what you want.
Yeah, okay, so now again we could say, well, gee, apparently if we use a wire that has some very high resistance, well, then we are going to waste half of the power in the resistor, right? If we use some kind of a lower resistor, maybe an ohm or so, then we still, apparently according to this equation, we lose half of the power in the resistor, and only the other half, or energy, the only other half of the energy actually ends up on our capacitor, right? That's a bad thing because, for example, if this is some kind of a toy, over here is an alkaline battery that we paid good money for, and over here is our capacitor that's in the toy, in that little helicopter, whatever it is, and that we want to fly, and we want to charge it, right? And half of it is somehow burned up in that resistor. Well, isn't there a better way? If we somehow would end up with the resistor well, zero resistance kind of hard to make, right? Zero, but very, very, very small. Would we do better? Yeah. No, apparently, no. And it's actually important to calculate these types of results because if we just look at this, if we just look at the circuit, we might say, if you have a big resistor there, well, big resistor, there's a lot of dissipation there, we should lose a lot of energy, that sort of makes sense, right? But if we make that resistor really small, how can it dissipate so much energy? Well, the mass is a really good thing, right? The mass tells us, doesn't matter, half of it's gone. Yes?
V1 isn't that
V1 is just the voltage of the source, right? The power delivered by the source is the voltage of the source, which is V1, times the current that's flowing. Yeah. You have a question?
The resistance is the reason it doesn't matter that the higher current that a lower resistance still dissipates the more energy because of the whole squaring thing there.
Right. I mean, the things apparently they just compensate. In fact, when I change the value of resistor R1, there is one thing that changes. What does change? Exactly, right? If I have a very large resistor, it takes forever to charge this thing. For a very small resistor, it takes very little time and anything in between, right? And so I may, in practice, choose the right value of resistors so that the battery doesn't get too hot during the charging process or whatnot. But yes, apparently it is. If I have a very small resistor, well, the current is very large, but it flows for a relatively short time. If I have a very large resistor, well, then the current is very small, but it flows forever. And in the end, if you do these integrals, get the same. Remarkable. So I thought that this was a really nice example where we could get some insight again, and it's actually a surprising result. Of course, there are lots more applications of circuits with resistors and capacitors, and so we're going to look at some of them here. So one of them is, again, this touch sensor. So suppose that I make some kind of a circuit again where, let's say I have a source that I somehow ramp from 0 to 5 volts or whatever it is, and then I have a resistor and a capacitor, and here this voltage across the capacitor, right? So how is the voltage going to look like across the capacitor? Well, we said that already. It's going to look like, well, it's already plotted here, right? Okay, so now suppose that this guy here is actually a touch sensor. It's a capacitor that if I put my finger on top of it, the value increases because our finger is made out of water. Sorry about that, right? But just water, big bags of water. So what's going to happen? How is the shape of this curve going to change? The red curve that we've plotted here already, how is it going to change? When we reduce the capacitor, it goes faster, right? Yeah. If we make the capacitor bigger, it goes slower, right? Tau is equal to R times C. Well, if we increase the capacitor, that tau, that time constant, is going to get longer. And if you look at the equation, well, the longer time constant means that the whole process still happens exactly the same. We still have that exponential, but now it takes more time. Okay. So how could we use this to make a touch sensor? Well, what do we want to do in a touch sensor? We want to figure out how big the capacitor is. Well, there is apparently a difference. It takes more time if the capacitor is big. So why don't we do the following? We set some voltage, for example, 3 volts, right? And so at some time t equals 0, we turn on our source, okay? So then at time t1 is when we reach 3 volts without the finger present. Now at some other time that is longer, t2, we also reach 3 volts when the finger is present. So if we somehow had a contraption that could measure these times, T1 and T2, well, we afterwards easily could determine whether no finger or a finger is present by simply comparing these two numbers, right? You're going to do that in Lab 6. I told you that you will have to build a touch sensor, of course. So in Lab 6, you're going to do that. You're going to use a microcontroller to turn on and off these voltages and so on. And actually, this one, it works a little bit different. It actually works by first. I write here. First, we charge this thing up all the way to 3 volts, and then we are going to discharge it through the resistor R1. This actually is an exponential. That's a nice scope. We're going to discharge it to 1 volt or so. When we reach the 1 volt, we turn off a timer in our microcontroller. We'll have to talk a little bit about microcontrollers at some point. They're important, right? And then we have that time T1. Now, of course, if suddenly you put the finger there, well, then it's going to look like this. And then the time is much longer. This time here is much longer. And based on that, you can determine whether a finger is present or not. Very simple. You had to solve a differential equation, but even that wasn't too hard. Okay, so another interesting thing is if you want to do, for example, communication, if you want to get information around. Well, there are 2 ways to get information around. One way is to simply send around the voltages, right? Let's say the sound that goes from your amplifier to the speaker is an analog voltage. It really just mimics exactly the pass that the baffle or the membrane of your speaker should make, right? And so if it should move really far over, then the voltage is high. If it should go the other, voltage is smaller, and so on. Okay, so those are analog signals. VGA, the VGA cables or to the monitors or so that you use, they're also analog signals, audio analog signals. But then there's digital signals where we basically, usually we encode all of our information as 1s and 0s. So 1 volt is a logic 1, 0 volt is a logic 0 or something like that, right? And there are lots of examples for that also. Ethernet, USB, HDMI, and so on. They are all actually digital signals. Well, you know, you can, if you're a mathematician, that's sort of where it ends. For a mathematician, a digital signals is 1s and 0s, and that's it. But when you're a circuit designer, lastly, these 1s and 0s, hey, what are they? Voltages or currents, so usually voltages, right? But could also be currents, could be charges or whatnot. Right? They are real signals. And is there such a thing like a voltage that can only, a wire can it have that has only voltage 1 or 0 volts? Well, no, of course. If it was 1 volt and now we want to go to 0 volts, well, we have to go through all the voltage values between 1 and 0, and probably that's actually even going to take some time, right? So let's look at that. So first of all, here is a picture of some cables, these sort of thicker coax cable. The way they usually made is that there is an inner wire, copper typically, and then around it is some kind of an insulating material, this whitish stuff. And then there is another conductor that is this braided stuff there, also copper. And finally, there is a final insulating jacket. Well, if you look at this and look at this from a circuit designer point of view, what kind of elements could you use to model this with? What does this look like? Is the only one awake today? Yes. Okay, where do you see capacitance here? Right, there is the inner wire and there is the outer sort of this braided jacket, and it looks kind of like a crooked, roundish pearl plate capacitor, right? Yeah, absolutely. I totally agree that there's got to be some capacitance. What else do we have in every wire? Always. There's some resistance. Thank you. I know you have the answer. Okay, so really what our wire or cable really looks like is there is some resistance, capacitance, resistance, capacitance, right? So of course it is distributed like this, right? Something like this. That's really what well, I could even have made it more accurate by putting resistors on both sides, right? That's really how our cable looks like. That's pretty complicated because there are lots of resistors and lots of capacitors. In fact, if we do this right, we need an infinite number of them, and then we have some other integrals to solve and so on. Of course, we have a class at Berkeley that goes over that. What class is it? 117. So, but fortunately for 40, there is an easy way out. Yeah, this is the real model, but this is good enough. Okay? If we model the cable just with one resistor and one capacitor, then, well, it's not quite accurate, and in some cases we make a real error, but in many cases this is fairly reasonable, especially if you have large source resistance and so on. Okay, so how does this affect communication? So let's suppose that we have a digital communication. So what would be that signal V1 look like? What would it look like? Yeah, it would be looking something like 0, and then it's going to be, what again? For example, 0 volts and 3 volts, right? And then it can be 0 again for a couple of clock periods, and then it goes up to 3 volts. Again, there would be a logic 1, a logic 0, logic 0, logic 0, 1, 1, 0, 1, 0, whatever, right? Okay? Maybe these are the bits that are now flowing to that server that capture this lecture, my voice, so you can watch it later again. Okay, so how is this going to look out on the other side? How's it going to look like, the other side? Yes. Yes. Well, here, nothing big, huh? It's 0 and it just stays 0. But then afterwards here, go up sort of gradually. And maybe it reaches almost the final value. And then it already has, maybe it doesn't even reach the final value. Then it has to go down again. Then it stays down for a little bit. It goes up again. Down. Up. Down. Something like this, right? That's really what happens. Of course, what parameter would you have to adjust in order to make this look more like a square wave? The red one? Yeah, it is tau, right? Tau, this is R1C1. If you make this really, really short, well, then the things happen. Still exactly what we plotted here will happen, but it will happen really, really fast. Okay? So if you make the resistance really small, then it goes faster. If you make the capacitance really small, it goes faster. Well, how would you make the capacitance really small? Make the cable shorter, for example, right? So, or make the diameter bigger. Put the stuff further apart, right? How would you make the resistance smaller? Use a fatter wire. Of course, one other thing that also now anybody has a system with HDMI. Well, the dorms are not that big, but if you separate your projector and the source, the DVD or so by far, you need a long HDMI cable. Can you have a 100 feet HDMI cable? Not going to work. Hey, we know why now, right? This tau gets really, really long, and the voltage simply doesn't reach the right value, and that's why it stops working when you make it too long. Yeah.
Okay, I can see when the voltage goes up to 1, the capacitor starts charging it. How does it discharge? Like, where does it leak into the air?
No, actually it's very simple, right? This voltage here, V1, is either going to be 3 volts, and that's the case where just that makes perfect sense, or it could be 0 volts. Well, if it's 0 volts, then the current simply goes this way through the resistor, and it dissipates probably in the resistor or in the source resistance. Yeah.
Does the Ethernet cable work the same way? Because I have a 100-foot Ethernet cable that doesn't have any problems. So I was wondering.
Well, different standards go for different distance. So Ethernet, first of all, the frequency on the Ethernet cable is much low. It's not that much lower. Yeah, Ethernet. Yeah, I think actually the amount of information over an Ethernet is less. Right? It's one gigabit per second, and they actually split it up into 4-wire pairs. If you look at an Ethernet cable, there's 4 wires. Okay, so they actually are smart. When you go, it used to be when 10 megabit Ethernet, they just used 1 pair. But now with 1 gigabit Ethernet, they actually use all 4 pairs, and so each pair handles only 250 megabits per second. In the HDMI cable, especially if you have these, 1080 standards or whatever, then the amount of information is much more. So the amount of information that has to go from your computer or DVD player to the monitor, so to the LCD screen, or so, is mind-boggling. Yeah, and so that's the reason why it's harder to get far with HDMI. Okay. Were there other questions? All right. So that's how it's going to look like. And of course, we can go and calculate exactly the waveform. We're not going to do that here. We just go. I just wanted to show you one other thing here that we now can understand, that the communication circuit designers use, a tool that communication circuit designers use in order to figure out whether a cable or whatever it happens to be, could also be wireless, whether that actually can communicate correctly at the speed that they want to go or not. And the way they do that is that they plot these transitions from 1 to 0 and 0 to 1 on a graph like this. So this is a transition from 0 to 1, and then it could, of course, stay. Well, let me highlight a little bit here. I'm not tall enough. So, for example, a transition from 0 to 1 would look like this, right? Another transition from 0 to 1 back to 0 would look like this. A third transition from 1 to 0 would look like this, and so on. Okay? So now, rather than drawing these nicely one after the other, like we've done here, you draw the whole thing right on top of one another. Okay? So whenever you start always at the same time 0, you say, I want to send out a pattern 0, 1, and you plot the thing. I want 1, 0, 0, 1, 1, and so on. You plot them all on top of each other, and there are even instruments that do this automatically for you. So this is data that came out of a lab, and there's an instrument that just plotted it. So now if you go sort of at reasonable speeds, then whenever the first transition, right, this is a 1 or a 0 here, and then this is the next transition, a bit could also be a 1 or a 0. Whenever, if you go reasonably slow, well, you pretty much reach the desired value at the end of your bit period. But as you start going faster and faster, well, then you don't quite get there anymore. And then these lines, they're starting to sort of fill in this area here. This area is called the eye. And so in order to quickly evaluate whether a cable, for example, can go at whatever speed it is, 10 gigabits or whatnot, communication circuit designers, they make this plot here, this is called the eye diagram, and then they look at this eye, and they look at how much white area there is. Well, if this area completely closes, you have absolutely no way anymore to determine whether you had a 1 or a 0. Here the eye is still a little bit open. It's not that terribly much open anymore, right? So you probably still can decide, yeah, this is a 1 and this is a 0 if it closes in more. If you go fast, it closes in more. The lines start overlapping. There's no way to determine. And then you know, well, my system doesn't go at the speed that I'm testing at now. Okay? So that's what's happening in our wires, and this is just one way of representing the information that is very useful to quickly determining whether we can go at a particular speed or not, and how well it works. Okay, so now, of course, we can also throw a little bit of math at this. We could say, for example, we could make some kind of a criterion. We could say that, well, we define as the maximum speed the speed at which we still reach 90% of the final value. Okay? So then, what we basically are saying is that, let's say again that we have a transition, could be from 0 to 1, or it could be from 1 to 0. It turns out they're totally symmetrical, so it doesn't really matter. But we want to go to, right, if this is 100%, we want to go to at least 90%. Okay? So that's actually here. And so then this is the time t that it takes to get to 90%. And then how fast can we go? How many bits per second can we? Yeah, the speed then is 1 over t. Okay? And so now we still we have to figure out what that is. Well, what is this curve here? What's the shape of this? Well, that was v1 times 1 minus e to the minus t over tau. And tau is RC. And at t equals capital T, this is equal to 90% of V1. Now, solve for T. Okay? All right, so we'll leave the rest for another time. All right.